All right, everyone. I am here with David Carmona. David is the General Manager of Artificial Intelligence and Innovation at Microsoft. David, welcome to the TWiML AI podcast.
Thank you, Sam. Pleasure to be here with you.
It is great to have you on the show, and I'm looking forward to digging into our conversation, which will focus on AI at scale and large-scale language models and a bunch of really interesting things you're doing there. Before we jump into the topic, though, I'd love to have you share a little bit about your background and how you came to work on all this cool stuff.
Yeah, well, I've been in Microsoft for almost 20 years, 19 and a half.
Wow.
Almost getting to that magical moment. And it's funny because my beginning with Microsoft, I was attracted to Microsoft. That was 20 years ago, so that was the big Windows moment, right? But actually, I didn't come to Microsoft because of Windows. I came to Microsoft because of at that time, my favorite product, which was Visual Studio. So I was a developer. I still am a developer. I will always be a developer, no matter where I am. And for me, working in Visual Studio has been like my entire career. So even if I started with AI and VR, probably way too early, that didn't end well. So I ended in traditional software development, and I had a ton of fun with that. And when I moved, I'm originally from Spain. When I moved here to the US to Corp, I worked in Visual Studio. So I ended managing the business for Visual Studio and all our tools like .NET and all of that. And it was a super fun time because it was that big transition in Microsoft to open development. So I was lucky to do things like launching TypeScript, right? Or open sourcing .NET, or making it cross-platform, or releasing Visual Studio Code, right? So super fun stuff. But then, like 5 years ago, this AI thing started to become super real. So I was offered to lead a new team in Microsoft focused on the business, on creating a new business for AI, and I didn't think about it twice. So yeah, that's where I am. So it's an interesting. So as you can see, my career is always like between technology and business. I think I mean, knock on good, but I think I'm in a right balance right now. So I have both. I'm super fortunate to have both because I work connecting with Microsoft Research and the entire organization of technology and research in Microsoft. And my team's goal is really to connect that with the business. So we work on, we define as themes, so like bigger themes of innovation in Microsoft, and then we connect those themes to actual real products and technologies that we can take to market. So it's super cool. And one of those things, we have many, but one of them, I think, like probably the start of the themes is AI at scale.
Okay. And so is the role primarily focused on taking innovations that are happening in research to existing Microsoft products, or is it more focused on creating new business opportunities, or is there some balance between the two?
Yeah, it's a balance. So we always we have the way that we work in Microsoft on our framework for innovation is based on horizon. So we refer to them as the three big horizons, right? So we have Horizon 1, 2, and 3. Horizon 3 are like the moonshots, right? Like longer term, new business creation, new category creation for Microsoft. A lot of that is driven by curiosity in most cases in research. So we leave a lot of room for researchers to work on those themes. But then we go all the way to Horizon 2, which are things that are really about opening new opportunities or creating new opportunities for existing products. And you can go to Horizon 1 even, which is extending existing products, right? So making them better. So we work in that balance between the three.
Nice. And so you mentioned AI at scale as being one of your big focus areas. What exactly does that mean at Microsoft?
Yeah, so AI at a scale, I mean, we named that as a new category. So it's not that it's a product or anything like that. So it's how we refer to what we believe is a huge change on the way that we are going to see people developing AI. And it's driven by many different things, many different trends and technology breakthroughs. But I think the most important one is this concept of massive models and what they mean, right? So this ability to create now like these huge, massive models with billions of parameters. And beyond the technical achievement, the reality is that those massive models are opening new opportunities that go beyond the technology and get into the business, right? So we can discuss that today. So so we can spend a lot of time on the technology behind it, and then we can focus a little bit on, hey, but what does it really mean? So how is this going to change the way that any company can develop AI, right? And this is really interesting. And then there's a whole ecosystem around this concept, like that you need to, for example, train these models. You need an AI supercomputer. So that's another piece of the puzzle, right, for AI at scale.
So we talk a lot about the increasing size of models, and particularly in the context of NLP and language models, but help us contextualize that. We throw around millions of parameters and hundreds of layers and things like that. How is it shaking out, or how do you think of this progression towards larger size models?
Yeah, I think in a sense, you probably remember the ImageNet moment for deep learning, right? So that was, I mean, many people are referring to this moment like the ImageNet moment for NLP, right? So because we get to a point that there's something that allows us to increase the size of the model, so we go for it, and then we see, hey, wait a second, this is getting better. So the more parameters that I add, the better that this is getting, right? So that was the moment in ImageNet with ResNet, for example, right? That we added so many layers, and hey, this image classifier is working so much better. So we are kind of in the same place, but at a totally different scale, right, of order of magnitude. Right? So you think, for example, that model, the ResNet model for ImageNet, I think it had like 60 million parameters. I mean, completely different domain. That was computer vision. Now we're talking about billions of parameters, and when we see the progression, it's being like very, very quick. So if you see, I don't know, GPT-1, so the first version was like 100 million parameters. Then I think BERT was like 300. Then you have Turing NLR, I think at that time was like 1.2 billion. Then you have GPT-2, 1.5. Then you have Turing NLG, that was 17 billion parameters. That was last year. We're not talking months ago. We're not talking about years ago. And then we had just a couple of months after that, GPT-3 with 175 billion parameters, right? So every step is 10 times growth. It's a new order of magnitude, which is super impressive.
So we've kind of transitioned from, in the domain of vision, we would always talk about the number of layers as an indication of the size and complexity of the model. And now when we talk about these language models, we tend to talk about parameters. What is that, and how does that tie to the architecture of these models?
Yeah, I mean, it's not that we didn't want to build these massive models before; it's that we couldn't. That's the reality. And I think that the big breakthrough to really enable this size of the model is the transformer architecture. And yeah, definitely a lot to say about that. But yeah, the transformer architecture, it has. I mean, it's also based in layers. In this case, they are like symmetric, so it scales very well. Because it has always the same number of inputs and outputs, so you can stack up all the layers. And it was a huge change, because the problem, the blocker that we had before with scaling these NLP models is that we were using techniques as recurrent neural networks, like LSTM and things like those. And those things are great because it allows you to connect for example, in a text, the words between them, you can have some kind of memory. So a word right now can be impacted by words in the text before, right? And you keep that memory. The problem is that the way that we were doing that was very sequential. So, by definition, a recurrent neural network is taking the previous step as an input. So you need to finish that step to go to the next one. So that impacted a lot on the scalability of the model. So I think with the transformer architecture, we kind of broke that ceiling because now suddenly we don't have an architecture that is recurrent. So now in this case, it's all in parallel. We take all the inputs in parallel, and with some techniques in particular, I think the most important one, or I would highlight two, but definitely for that to work, two things had to happen. One is the concept of the positional embedding. So how every word needs to get as an input in the model the position, somehow a flag of an indication on where that word is, because that's of course important. It's very important where a word is in a sentence to understand the sentence. But then the second thing is this concept of attention, or in this case self-attention, which is a way to kind of replicate that concept of connecting or changing the meaning of words depending on the words that were happening before, or even in the case of bidirectional transformers, words that are happening after that, right? And that's a whole new concept applied to NLP that is proving to be not only super scalable, but even performing even better than the traditional approach to NLP.
So how should we think about how attention works in these kinds of models?
So I mean, it's a very simplistic view, but I like to think of it because attention is not new. So we've been using attention in other domains, right? Like vision or image generation, or even. I mean, the most simple example that I use all the time is movie recommendation, right? So how do you know if a user is going to like a movie or not? So the way that you do that is that you take a vector defining the movie in any dimensional space, and then you take another vector defining the taste of the user, and then you multiply those vectors, right, to get the distance, the cosine distance or similarity between those two vectors, and that's an indication of how much the user will like the movie. That's attention, but in this case of two different entities, right? My taste and the movie. In this case, self-attention is like doing something similar, but with the sentence with itself, or with the text with itself, right? So, but in this case, the attention that we want to measure is the connection between the words. So how one word is related or connected to the rest of the words. And at the end, you're going to have like a heat map, right? So where every word is connected in some manner with other words. So if you are saying the kid hit the ball and he was happy, so he will be super connected with boy, right? So that I mean, it's super simple because at the end you have multi-headed attention blocks, and then you have all these different layers. It's like trying to understand convolutional neural networks after 3 layers. You lost. You are completely lost on what's happening there. But I mean, that's the core principle of it.
It's part of what's interesting here is that we've transitioned from an approach to NLP that was, like you mentioned, prior to capturing positionality. We take a bag of words of things that was at the document level, didn't capture where those words were, didn't really do a good job of capturing the relationships, but we're just looking at the statistical properties of a document or sentence or corpus, to now looking at the relationships between all of these entities that make up language. Is that part of the power of this?
Yeah. Exactly. I would say that, and then the concept of training these models with self-supervised algorithms, right? So with self-supervised training, I think that's the other thing that was the explosion in all these models is how now, because this scales amazingly well, now you can afford training these things with huge amounts of data. like, for example, the entire internet, the kind of, right, which is kind of what we're doing with this model. So we take the text in the entire internet, and then depending on the model, and we can go in a little bit more detail in there, if it's a generation model or a representation model, with smart techniques, you just take that, you mask that test, so the model can try to guess either the missing words or the words that are happening after a given text, and by training that with that input that you are almost not touching at all, right? So it's all self-supervised, unlabeled, and all of that. The model can actually learn very complex concepts and relationships.
Mm-hmm. You mentioned different types of models. Elaborate on that a bit.
Yeah, so I think the way that, and we can talk then more about, because then this same concept can apply beyond NLP, but if we focus just on NLP, there are two main families of models. One is the one that I think people are super excited, also because of Turing NLG and because of GPT-3. Those models are generation models. So they are natural language generation models, or NLG. And in that case, what the way that model is trained is they are called autoregressive models, because you train the model with a lot of text, but then you train it to guess what is going to happen, what text goes after a particular text, right? So they are super good generating text. Guessing at the end of a sentence, or guessing an entire document, or guessing how a movie will end, or whatever we want to guess, or summarizing text, things like those. That's one big family of models. You have again, like GPT-3 is an example of that, Turing NLG is an example of that. And then you have another family, which is more about representation. So natural language representation models. And the goal of those is more representing the text. So in that case, the architecture that is used, instead of trying to guess, or the way that it's trained, instead of trying to guess what's next, what we do is that you mask some words in the text, and then the model will try to guess it. And they are called bidirectional, because in that case, not only they look at what happened before a certain moment, but also after that. So they will look at the words before and after a particular word to understand the context there, right? So those are really good to map like text to a representation that then I can fine tune to do whatever I want, right? So from super basic sentiment analysis to question answering, or whatever I want to fine tune the model. So those are like the two big blocks. Then I like to go a little bit deeper, because for each of them, there are two other families that I think are very relevant to understand, which is how, so at the end, there's more than one language in the world, right? So you need to address that, right? So in particular, where you are creating a real product, so we are using these models in Office, for example. Office is working in I feel like 100 languages. So imagine doing this for every language would be very difficult. And that would be the traditional approach of doing this. So and Microsoft has been a big believer on the need of doing this thing in a universal way. So that creates a new family of models that are universal models, right? Universal language models. And in the case of Turing, for example, we have both. We have a regular model, and then we have the universal language representation, ULR. So Turing, ULR, universal language representation. And that is super powerful, because what allows us, for example, in Microsoft, is that to implement features in Word using this, like, semantic search. We don't need to train that feature or that model for every language. We just need to fine tune it for one language, and then you have the feature for free in 100 languages, right? Which is super cool. So very, very recommended to use those models for that. This was, by the way, for people who want to go deeper. There's a paper that I like a lot. I think it was in 2017, where it explains this concept, and the example that it uses is how you learn math, right? So you look at, well, not me. I wouldn't consider me bilingual. I speak Spanish and a little bit of English, but my kids are truly bilingual. And when they learn math, they don't need to learn that 2 + 2 = 4 in English, but then dos más dos cuatro in Spanish, right? So they just need to learn math once, and then they can apply that in different languages. So it's the same thing for models. So you can focus on teaching or training the core concepts, fine-tuning for the concept, and then you have it for free in all the languages.
Yeah, I want to dig into transfer learning and multitask. These are all things that are coming to mind as you're explaining this. But before we do that, we started out talking about language models as an example of these massive models that require a new way of thinking about AI at scale. And you mentioned the progression of the sizes of these models, and it's 10x each time. GPT-3 is 10x Turing. And one question that occurs to me is, is size the most important or the only factor? Does it mean that each time we jump a generation, let's just forget about we shouldn't be using Turing anymore. Let's just use GPT-3 because it's 10x better? I think, there's some obvious reasons why that might not be the case. Like if they're trained on different corpuses, like we know that GPT-3 has kind of a very broad public internet, and at least with GPT-2, like there was a lot of critique about, Reddit, and the biases that get introduced there. So the training set is going to be an obvious differentiator that's separate from the size. But I'm wondering if there are other things that we need to be thinking about beyond just the size of the model.
No, you are right, and I think so. It's a very simplistic thing to just discuss the models of or the parameters of a model. There's way more. I have to say though that the one thing that we are seeing is that the more parameters that you add right now, we are not seeing like the ceiling of this. So we keep improving the accuracy and the generality of the model. So hey, parameters are important, but then at the same time, it is true that it really, so there's not one model for everything. So different models are good for different things, right? And in our case, for example, we Turing, our family of models is actually a family because of that. So we don't believe that one model will, at least right now, will be useful for every single scenario that you are targeting, right? So in our case, we created that family of model, which are inclusive of many things, including many different language, like this basic classification that I was providing before, or this metrics of different models. You're going to need a model for each of them, depending on what you want to accomplish. But then even beyond that, because not everything that you do is NLP. So in the family of Turing in Microsoft, we have models that are even multimodal, that are including image and text, or that are focused on image, and that thing will keep growing. So that's something important to keep in mind. The other thing is, of course, the eternal debate on the importance of the architectures, right? That you're using. So I think there's I don't have a super strong opinion. I think it's like everything. It will go through phases. It will get to a moment that just by adding brute force parameters, the thing will be very difficult to improve, and we'll need to be a little bit smarter on how we can improve those models. We can optimize those models in another different way. But again, I don't want to diminish the fact that we keep seeing that we add more parameters and we get more power, right? One thing that you said, though, Sam, I want to double click on that because it's super important. So it's the responsible AI implications of the model. I think that will be an area for models to differentiate and to keep in mind when you're using a model, because the reality is that right now these models they have a lot of challenges, from the bias, transparency, and others that we need to keep in mind. So we need to, just as we innovate on the power, accuracy, multitask aspect of the generality of these models, we also need to innovate on the responsible side of them. And as you said, the training corpus, that's important. I think right now we are probably way too late in the pipeline to apply responsible AI principles to these models, meaning that we create things with these models and then we apply those things like, I don't know, like filtering or many other techniques that you can use there. I think we need to go earlier in the process, even at the point of the training, so we can make those models responsible by design.
Do you have a sense for how we can do that? A lot of the power of these models comes from essentially taking the entire internet and building a language model based on it, or large parts of the internet. How do you apply what are the techniques that we can use to build responsibility in earlier at that scale?
So just as an example, but one example in Microsoft could be the Office or the Outlook auto reply. Right? So that is the typical example of a massive NLP model that is taking as an input an email, and as an output is creating a likely reply that you want to do. Right? So that scenario on paper, it looks so simple, extremely simple. But when you get into the responsible side of it, it's extremely complex, and you need to pay a lot of attention. And it's not like a one-shot thing that you do and done. You are golden. The reality is that you need to apply that across the entire life cycle of the model. From, as you said, so you mentioned one that is important, which is the training data. So yes, of course, we need to get a subset of the training data to make sure that there's no toxic data that is training the model, but that is not enough. So we need to keep in mind things like the privacy of the user, right? So think of how can we. So actually, for this feature, we use differential privacy to make sure that the instances that we surface, they are not. They cannot identify a user or things like those, and you can think of. Also the output as something that we also manage, that we make sure that they are short answers, that they are not like long emails, of course, things like those. So it's something that you need to do at every stage. There's a ton of active research happening right now to really tackle this super complex challenge that we have with these models.
Mm-hmm. But before we jump into how we achieve this kind of scale, you mentioned something in our pre-call that really stuck with me. It's this idea that models are becoming a platform, and transfer learning is a piece of that. Fine tuning is a piece of that. I'd love to hear you riff on that idea. I think it's a really interesting way to think about models.
Yeah. I mean, it's not a new concept. So definitely we've been seeing. So you see our services in the cognitive services in Azure, and they all support the concept of transfer learning. So you don't need to train a model from scratch, right? So but the reality is that a lot of what we do in AI is training models from scratch for your particular scenario. So we're doing everything that we can to try to simplify that process, because if we don't simplify that process, it's going to be very difficult to really scale AI in an organization, in a company. So there are definitely many techniques to do that. I think in the area of NLP, fine-tuning is the most relevant now, and then we can talk about some emerging ones that are super interesting and cool. But with the fine-tuning process, the idea is that you can use a model that is pre-trained, like our Turing model, pre-trained on vast amount of information from the internet, multi-domain, totally general, and then you fine-tune that model. So fine-tuning meaning adding something to it. Like, for example, if you want to fine-tune the model to do a sentiment analysis, so you would add at the end like a classifier or something like that, a binary classifier, and then you use label data. In this case, you use like sentences that are, positive, negative sentiment, and then you fine tune. So you train additionally. It's like extra steps of training of that entire thing with your added classifier. In this case, for example, which is going to update the weights, but it's not starting from scratch, meaning that you don't need that massive data, the skills, because you don't need to change the architecture. You don't need the compute because it's not that much compute needed. So that is certainly a huge step into democratizing this model, right? So that's super important. And not only you can do that for fine tuning for specific tasks. You can also fine tune it for your domain. So if you work in finance, or you work in health, or you are in any industry, and you want to find a law company, so you want law firm, you want to fine tune that model for the domain of your vertical. So you don't need to train the whole thing. You just need to train for that particular domain. So super, super important. But then what we're seeing is that these models can go even beyond that. And that's a super interesting area right now. It's still, in the beginnings, but what is the big difference with that approach? So in this first approach with fine tuning, you are training the model at some point. I mean, not from scratch, but you're training it. You are changing the weights of the model. You're updating that model. You need compute to train it. But then we have these other techniques. They are called like zero shot or few shot, where you don't do that. So the model can learn in runtime. So you don't need to change the weights of the model. You have only one model. You don't change that model. Now, in runtime, where you are doing the inference of the model, you can, if you are doing a few shots, then what you do is just you provide a few examples of the task that you want to do, and then directly the one that you want to solve, and the model will do it, which is mind-blowing that it can do that. But then you have zero shot, which is like the mind-blowing times 3, which is that you don't even need to provide examples. So you can ask one of these models, hey, I want to translate this to French. And you provide the sentence, and the model will know how to do that. It will identify patterns in the corpus data that was trained on, and it will know what it means to do a translation, and it will do that translation. So those techniques, what they are really doing from fine-tuning to few shot to zero shot is making it much easier to really use these models in your particular scenarios for your particular domain, your particular task, or your particular modality. Super cool.
Awesome. So let's dig into we've talked about kind of models. Just a few quick words on applications, like the language. What do you think are the most exciting applications of language models generally, or Turing in particular, within and outside of Microsoft?
Yeah. So what I can do, because it's it's a big one. We can talk for a long time. I can give you like an overview of how we are using it in Microsoft, and then you can get a sense of the usages that it can have. So in Microsoft, the way that we look at this is like we always look at these things. Any technology is a stack. So our goal always is to deliver a full stack. So you have, and that's our approach to any technology. So we do the research, but then we want to make sure that research is available for others to use, and then we want to make sure that we keep adding layers. For example, the first one would be releasing that as open source, right? So we add another layer. We want that to be part of Azure, so you can train those models yourselves, which is the AI supercomputer that we are providing in Azure to train those models. But then we keep building on that. On top of that, we add things like Azure Machine Learning, so you have another abstraction layer that can improve your productivity, fine-tuning those models, like the approach that we were mentioned before. But then we put another layer on top of that, which is cognitive services, which are end-to-end, out-of-the-box services that you can use as REST endpoints, and you can infuse directly into your application without worrying about doing anything with those models. And then on top of that, we build applications. So we build we make them part of our products like Office, Dynamics, or we create new products that weren't possible before. So that's our entire approach. I think if we focus on the application side, just to give you some examples of things that are already available that people can use that are powered by these massive models. A lot in Office. A lot of things in Office are powered by these models. So you can think of, for example, semantic search in Office. So you open a Word document, you search for something in that Word document, and that is not the traditional find and replace that we had before. This is semantic search. So you can even ask questions to the document, and the document will answer those questions. That is all powered by Turing. You have things like document summarization. So you go to SharePoint and you hover on a document, and you will see a summary of the document in there. That is an abstraction, so it's not just taking parts of the document. That is generated with Turing. Things in Outlook, like Outlook auto reply that I was mentioning before, or things like there's something called meeting insights, that before a meeting it will give you all the relevant information about that meeting. So those are like in the taxonomy that we were talking before. Those would be Horizon 1. Is about making those applications better. But then we have these Horizon 2 things that are new opportunities that these models can open. And I think a good example of that would be Project Cortex. So Project Cortex is part of the Microsoft 365 family. And the goal of that project is super cool. So what it does is that it's able to get all your internal knowledge in your organization by looking at both the structure and the unstructured data in your organization. So think of documents, meetings, PowerPoints, anything that you have in there, even images, because it's able to scan and doing OCR on images. So it's able to crawl all that information from your company and then to extract knowledge out of that. So what we do is that we create this concept of a knowledge entity. Like imagine that, you are in a law firm, imagine international, whatever, commerce, I don't know, I have no idea of law. But it's like a topic that then the AI system was able to extract from your information, and it can help you a lot. So it can provide you a summary. It can give you what are the most relevant documents for that particular subject in the company. What are the experts? So who you should talk with about those topics. So it's mind blowing knowledge basis, right? So that you can get is like extracting the DNA of your company, so you can really make it available for the rest of employees. And like those, I can bring any product that you can mention. We are using Bing, so it's another, of course, super important one. Things like question and answer in Bing, even the universal search. So we use this trick of universal language representation in Bing, and those are all available in there as well. So we use it for the number. Then more on the business side, I would mention. In Dynamics 365, we use these models for a lot of different things. Very obvious one, of course, is anything that has to do with customer service, like customer service understanding or sentiment analysis, all of that in customer service that is powered by these models. But then things that are more visionary. So think of, for example, in Dynamics 365, one of the things that we can provide is like suggestions to sellers in your company by looking at any interaction with that customer before, like emails or documents, phone calls, whatever, right? So it's able to understand that unstructured information and give you, it's like a language generation, but in this case to as next steps to your customers. So yeah, super, super broad. We could talk for a while, yeah.
So let's maybe jump into, what's happening that's enabling all of this to take place now. One of the things that, when we think about kind of the scale and size of these models, we've talked about the scale of the compute that has been required to enable it. How do you think, and you mentioned AI supercomputer, like what's that all about? How do you think about building out the infrastructure to scale and train these models?
Yeah, let's say that to train a model like this in your laptop will take probably thousands of centuries. I think so. Definitely, you need a lot of scale to train one of these. And you need. I mean, it's amazing the kind of challenges that you get when you grow a model like this. Like fundamental challenges, like hey, the model doesn't fit in your GPU. That's something that we weren't used before, right? So I think it is like if you go past 1.3 billion parameters, something like that, the model is not going to fit. So you better find new ways. But then it's just the compute. So the time required to train one of these models, you need like ultra parallelism. And I think so. That's the main reason of why we focus on, and like always, like I was saying at the beginning, we try to have a platform approach to it. So not thinking of fixing this problem for Turing, for our models, but fixing this problem for our customers so they can use this infrastructure as well. So the approach that we took was building this massive infrastructure in Azure. So these are massive clusters that you can spin directly in Azure. And not only you can spin, then of course, you have the complexity when you have these are, I mean, imagine, for example, the one that we announced a year ago, that is a massive cluster of like 10,000 GPUs. You have more than 200,000 CPUs. So it's massive scale. So how do you manage that? You need things that allow you to manage that in a distributed way. And then what is even more challenging is, okay, so I have my infrastructure completely managed. I can spin, stop. It is integrated with Azure Machine Learning. So you can like launch like jobs in that massive infrastructure. But then how do you actually do it? So you have a model that is, by definition, is huge. So how do you train that thing? How do you divide this task, this super complex task, into individual nodes in your massive cluster? And that's the other side of the coin, which is our work on these like software systems that are meant to help you in that process. So this was at the same time that we announced the AI supercomputer. We also announced it's called DeepSpeed. It's open source, so you can use it on top of anything, and it will help you do that for you. So what it will do is that it will take this training and it will distribute that training across a massive infrastructure. So it will know how to do that in an efficient way, and it does it basically. It's like we call it a 3D distribution because it takes like three different axes to let's say chunk this task, right? One, which is the most basic one, is the data distribution. So you just split your data in smaller chunks, and then you have each node is going to take one of those chunks. But that is not enough. You need to go further than that. So the other level of distribution that we use is the pipeline distribution, which is because of the transformer architecture, that like symmetry is relatively easy to split the model in the different layers. So each node will take a different layer, and then there's a lot of communication and optimization going on there that you need to take care. And then the last one is the model parallelization, which is then even for each of those layers, we can divide in smaller chunks, and each of them going to a different GPU. So at the end, what that allows you, with a lot of work, so there's a lot of research involved in this framework, is that you almost get like a linear distribution, like a linear growth in your model. So you can see by the number of parameters. And by the way, this thing is able to take more than 1 trillion parameters. So you can train models that are not even existing today. And you see the line, and it's almost linear. So it's exactly what you are looking for in the systems.
Oh, wow. And what about on the hardware side? Microsoft announced this Brainwave project some time ago to bring new hardware architectures to bear to this problem. Can you share a little bit about that?
Yeah, so yeah, we announced maybe a little bit more ago, but it's fully available now. So you go to Azure and you go to Azure Machine Learning, and one of the options that you have to deploy your model is FPGA. And what that is going to give you, especially in inference time, is very low latency and a lot of efficiency in costs, right? So it's perfect for massive. I always use the same example. So this feature in Word, one of the features powered in Word by Turing is called predictive text. So that means that when you type, it's going to give you suggestion on how the text will continue. Right? So think of it as the auto intelligence, but for Word. 300 million users of Word. Imagine doing the inference of that model in every keystroke. So that's the scale that we're talking here. Is huge. So you better optimize that a lot if you want to scale it to that number. And we do that. I mean, you have to do it in again. It's like a game that you have to tweak every single step. Of course, we don't go with these multi-billion models on inference time. So there's a lot of optimization to do there to reduce the number of parameters, to even using like techniques to make it more efficient. And then there's the hardware, right? So we use the Onyx runtime in Microsoft that can optimize not only for CPUs, so it has optimization for CPUs, but also for FPGA. So it's a way of abstracting you from the hardware that you have underneath. And it really allows you to bring all these things that are great to talk from the research point of view, but then putting them in action, it requires all this level of detail that is a new level of complexity.
So that's primarily focused on the inference side. Do you see any are there any particular innovations you're excited about on the hardware side for training, or do you see it primarily being evolutions of today's GPUs?
I mean, when we see, I mean, it's super evolving. So we'll see the reality right now is that you have to be flexible. So we are not discarding any approach, any at all, right? So the reality is that FPGA for the inference was super efficient because it allows you to change it, right? So it's programmable. So that was very, very efficient for that side and very agile. The combination of agility and efficiency was the right thing, but that may change at any moment. And as these things get more stable, then ASIC may be the way to go. And yeah, of course, we're not discarding any of those approaches.
So how do you see this level of scale that we're dealing with today impacting the world for kind of users of AI? What changes?
I think that the main thing, maybe bringing all of this together, is how this will change the way that you develop AI. So how this will open new ways of developing AI that we can use right now. So that whole concept of creating more general multitask, multi-domain, multi-modality models that then you can customize for your particular tasks, that has huge implications on how you can scale AI in your organization, and how AI can scale to other organizations, like smaller organizations, right? So that for us is a huge aspect of all of this. And the way that I see it is that it's kind of what we experience in the last 20 years for software. It's very similar. So software, at some moment, we had the hard lesson that software has to be super connected to the business. So if you have a team of software developers in a basement not connected to the business, that is not going to work. I think AI is in a basement right now, kind of, right? So we are not fully connected to the business, and it's because it requires so much like skills, so many skills and expertise that it's a very technical domain right now. we need to change that. So we need to make sure that the business and AI come together. And we learned that with software. It's called DevOps. It's about bringing the two together and then doing small iterations on it. It's coming to AI. We are all talking about MLOps now. It's a huge area. It's our bet definitely in Microsoft to provide the platform to empower that collaboration and that continuous iteration and trackability of everything that you do in your AI development cycle. That will be massively empowered by AI at a scale. So you have models that can really empower like a more dynamic way. So you don't have to create from scratch these models. You can iterate on them with the business and just focus on teaching your domain to the model instead of starting from scratch. That goes in that direction. We do think that there's one step beyond that we are also seeing. We also saw with software that also needs to happen with AI, which is really going beyond the technology and the business and getting to every employee. So how every employee in our organization should be empowered with AI, just like they can use Excel right now to reason over numbers. What is the equivalent of that for AI? So every employee can apply AI, and not only apply, but also create, consume, mix and match. So having some level of freedom to really apply AI to what they do. That's another huge area, like the augmented intelligence area, that with these models, we may see it happening sooner than later.
Awesome. Well, David, it's been wonderful to catch up with you and to dig into some of the work you're doing around AI at scale. Thanks so much for taking the time to chat with us.
Thank you so much, Sam. It was a pleasure.
My pleasure.